Okay, welcome everyone to the 8th edition of PMIP Wings. It's our pleasure to host two eminent speakers today who will drag us into the deep, dark crevices of climate models that we need to go into in order to understand climate variability. So this is a climate variability edition of PMIP Wings, and the first one that's co-sponsored with the PMIP project, since we have two speakers from the German PMIP project today. And the first one is Tom Laepple from the Alfred-Wegener-Institut in Potsdam, and the second one is Bo Liu, who has disappeared off my screen, but she's here, and she's from the Max Planck Institute for Meteorology in Hamburg. And without further ado, I would suggest, Tom, that you share your screen and we start with your presentation. It's 20 minutes. After that, there's brief time for clarifying questions before we continue with Bo's presentation. And after Bo's presentation, which will also be 20 minutes, we have time for discussion, which again, I would suggest we do not record for data privacy reasons. So we stop recording after Bo's presentation and elementary questions for clarification. Tom, the floor is yours. Go ahead.
Thank you. So good morning. So the idea for this meeting or for this talk came up when we had a meeting from Pages organized on centennial climate variability, and I was rambling about that we still have this issue that proxies and models are showing us different worlds, and the modelers are not doing enough about this. And then I was invited to talk here and to make a title with that radical and new insight. And this is there we are. Okay, so why do I still represent different worlds? This is like a slide, or first the outline maybe. So first I would like to go back in time and then to present where are we now. I would like to see, can we say more than just that there's a problem? So can we maybe go a bit more into the structure, because it's needed to find the reasons for it, the question if that's relevant. And then finally, this is more your side, but I would like to propose some ideas. What could we maybe do from the modeling side to address this question? So this is slides I made 10 years ago to when this all started. And what this is showing us is here sea surface temperature reconstruction from magnesium calcium from one specific site. It's showing you the last 6,000 years. And you can see it's going down. And you can also see like variations up and down. And the whole, you have the trend downwards here. And now, if you take the same time series again, same location, same resolution, but this time from a climate model, at this time this was the ECAM5 MPUM simulation, then you can see it looks very different. And if you would look at this from a statistical point of view, the deviation in variance is a factor of 100. So now either you could put yourself on the side of the data, which is sometimes done, and say, okay, these ups and downs, they are really changes in local sea surface temperature. Then this would mean we really have a problem on the climate model side, because we would underestimate the variability by a factor of 100. Or we could put ourselves and say, okay, this is the reality and everything else is noise, but then we don't have to go to the ocean and take all these expensive courses. So that's a bit like where this started, and what we decided there is we need to get further into this. So we need to have, like on the proxy side, we need uncertainty signal models. We need to understand what the variability, which part we can believe and which part we can't believe, that we can really combine them and go into the quantitative climate research. And this is what we did in the past decade. So we did a deep dive into proxy records, and this is just showing you an example for people maybe who are more using proxies and not used to make them. This is showing in Antarctica a trench. So basically you dig out, and on the side we are taking the water isotopes. So the water isotopes are proxy for temperature. Red means warm, blue means cold. So these are like 20 years down, and in a perfect world, you would now have red and blue layers perfectly horizontal. So this would be the climate thing you would expect. That's a seasonal cycle. What you see is that you have all these kinds of horizontal variations, and this in this case is one type of the noise. And it's very typical that proxies are quite have quite some noise components. But even and what you can do now, you can try to implement these processes into either something which is now called proxy forward models, or like numerical forward models, where you try to simulate what you understand about the proxy. Or what we also tried is to make it more on a mathematical side, that we could predict what is the effect on the power spectra directly from these effects, like noise, mixing in the sediment, and so on. But turned out that even with this research of our group, but also other groups, we didn't really find the magic bullet yet to get the proxy data consistent to the model data. So after we were able, or we thought we were able to correct the marine records, we published this paper. We found these large model data differences in the marine realm, and something similar is also happening on, as we will see, not just in the marine part. Now, what also happened in the last 10 years, that there was another paper coming out which said climate models can correctly simulate everything. So we had like this opposing question of, are we now having a problem? Are the models too sleepy, or is everything fine? And this is where, in a workshop which Kira organized some years ago in Heidelberg, we thought we would like to look at this again. And this is and write the current state where we are in this. And that's on a perspective paper which will come out like the next week. And we look into this question of where are we now and where do we go in this question. So what do we have here? We have these opposing or seemingly opposing results that on one hand, climate models can correctly simulate the temperature variability, but there's something important. It's global average here. And we have the result that we have these large differences. So let's look at this in examples. So what you can see here in the top figure, these are the time series of the last millennium. On one hand, from the models here, the PMIP ensemble in blue, and on the other hand, from the pages 2K reconstructions in orange. And you can see they track each other nicely, so they are following the volcanic dips here. And you can also look at this in the spectral domain. So and then here you have the time period in years, so interannual to multicentennial, and here you basically have the variance. And here you can see it's a kind of a scaling behavior, so you have this straight line thing, and they are overlapping each other, so everything looks fine. Now, if we look at the local scale, here now example of the Cariaco SST record, then things look different. So what we see now, that this record here would propose basically that you have that the variations are much stronger than what you have in blue. So the orange ones here, you have these deviations which deviate from this more or less straight line. And if you look in the spectral domain, what you can see is that everything is fine until, let's say, multi-decadal timescales. Here, the proxy is inside the models, but then on the long timescales, the proxy seems to shoot up. So you seem to have more variability on like centennial and longer timescales. Now, this is just cherry picking. I mean, there's just one example. So we wanted to not just only not do cherry picking on the records, but also not on the studies. So we did a literature review where we basically looked at the existing studies which argue to compare temperature variability in proxy records and climate models in the Holocene. And then for each of them, we took the author agreement and we made this nice figure. And I will just simplify the figure because then it's not so distracting. Okay, so what we can see here. We see an agreement scale, meaning that the authors meant it's agreeing in blue, or they mean it's disagreeing in red. And then each dot is a study. And you have two axes. The x-axis here, this is the spatial scale. This here, and the y-axis here, that's the temporal scale, and the y-axis is spatial scale. So we start at interannual scales and we go to millennial scales. We start at local scales and we go to global scales. And you can see already the background color, which is the mean, that it starts up rather blue on the interannual scale. On the fast time scales, we have this most of the studies argue we have an agreement between proxy-based reconstructions and models. But now, if we go on the local scale to the long time scales, then things are getting red. So that's what we saw before. So basically, most studies are proposing that really locally models are too sleepy. But if you go on the global scale, if you go up, things are getting blue again. So globally, things are quite fine. Locally, we have this mismatch, which is starting at the multi-decadal scale, and in between you have a mixture of these. So it really seems like it's not just our studies, but the literature has this finds a systematic disagreement on the local long time scales, but disagreement on the global scales. Now, this is, can we say more than just that there is this model data mismatch on the match on the global and the mismatch on the local scale? And for this, I would like to take you to the spectral domain again. And let's first look in the model world. And what you see here now is the power spectrum of temperature. So it's just the variance of the temperature compared to at a specific time scale, so interannual to millennial. And you can see this first for local temperatures, we get this line here. And for global temperatures, we get this line here. So what does it mean? It means local temperatures are more variable than global temperatures. We all know this. I mean, energy is redistributed around. If you go to the longer time scales, they are approaching each other. So what does it mean? Local variability is averaging out over time, and the local and the global are getting more similar to each other. And one can get more quantitative here. So it turns out that the distance between these two lines, this is a ratio because we are here on a log scale. So like having a distance of this length here means factor of 10, for example. So therefore the distance, so the ratio of the local and the global variability, you can translate this under some assumption in a typical spatial scale of an anomaly. So meaning like how big is a typical anomaly of nature or of, it can be from forced, it can be natural, whatever, but how big is a typical anomaly spatially? And we can see that this would predict that, or this would show that in the models, we are starting at interannual scale, the typical scale of like 1,000 kilometers, 1,500 kilometers, and we go here to a scale of 8,000 kilometers. So things are getting more global. And one can also visualize this very simply. So you just, if you take your model simulation and you just subtract 1 year minus another year, then you get one realization, so one example of a fluctuation on the interannual scale. And you could say, you see that these have like some typical spatial scales here, which is about the scale we're getting here. Now, if you take a decade minus another decade, then you see things are getting a bit larger, the spatial scales. And now in the models, if you take like 250 years minus another 250 years, then you can see things are fading out. And yeah, things are fading out and the scales are getting bigger. So that's basically what you see here in the spectra below. You can just play with your play by looking at these fluctuations. It's of course just like let's say it's a qualitative thing because you only look at a single fluctuation here, but it shows you a bit what is meant here by this graph. Okay, so this here is now the model world. Now I would like to see what the reconstruction from the proxies are suggesting. So I'm fading out the models as a grayish background now, and I'm putting on the proxy data. So first, we are putting in the global mean temperature. That's pages 2K, and we saw before the global mean temperature is quite consistent in terms of their variability with their model. So therefore, the gray and the red one are overlapping. So basically, you get the same line as we get before. So because proxies are consistent to the models. Now, if we go to the local temperature, we have on one hand like the pages 2K data from Ellerhoff and compiled here, and then we are having on the long time scales here on this part here. This comes from pollen records and from marine records corrected for non-climate variability. And so what we see here, basically that we are leaving, as we saw before, at some multi-decadal timescales, we are leaving the we are getting more variable than what the models are suggesting. So we are leaving this envelope of the models. And now, if we go again to this idea of the spatial scale, what does it mean now? That means that now the proxy data suggests that local and global temperature get parallel to each other. So what does it mean to getting parallel to each other? It means that our spatial scale gets stuck. So the idea would be that instead of the model, which suggests things are getting more global and global, the proxy data would more suggest things are getting larger, but then somewhere they get stuck, and your patterns might still things like, let's say, land-ocean boundaries or topographic boundaries, which are independent of the time scale, they might start to dominate, and you still have you still get patterns even on millennial timescales. And it also shows that it's possible. I mean, in the beginning, we are really suspicious. Is it possible that on one hand, on local variability could be underestimated so strongly, but global variability can be right? And turns out physically it's possible, or not physically, but at least from compared to instrumental data, it's possible, because in the part where we still have the instrumental data, where we know the spatial scales is consistent, and on the longer time scales, it just would mean the spatial scale gets stuck. So basically, instead of so we go from interannual to centennial, we get like smaller in our scales, but we would argue it could be that on millennial scales, we are still on the similar amplitude and similar spatial scale that what we have on the what we have basically on the multi-decadal time scales. Okay, so that's, I think, one evidence. So if we are looking for getting the models or seeing if the model would be consistent with the proxy data, it's not just about getting the absolute variability right, it's also maybe about getting the spatial scale of the variability right. The other evidence we have is latitudinal structure. So this is something that the studies from pollen data, but also the study here from marine data shows that if you compare, this is now there's not even a scale written here. Okay, so the vertical scale here shows the ratio between the proxy data and the model simulation, meaning that if we are below the red line, then the models are more variable, and if we are above the red line, the proxies are more variable, and you can see this kind of shape appearing here. So we have the biggest mismatch we're having in the tropics, meaning because the models are mainly, or the most of the variability on long timescales the models are simulating is limited to the high latitudes, and the proxies are suggesting, but you also have variability in the tropics. And finally, some more evidence I think we have on the structure of this variability is that if you look at this is now from pollen data, the variability compared to the variability in the models. So you see again on multi-decadal timescales, the pollen data suggests things are more variable than the models. But if you plot on the right side the sea surface temperature and the land temperature variability, then they seem to be parallel to each other. So I mean, the land temperature variability is higher than on the ocean by like an amplitude factor of 2, which is not so unrealistic. We see the same on like in global warming, but it's parallel to each other, meaning that it looks like it's more like a global, or we were arguing it's coming from the ocean, which is transferred to the land. It's not that the land would have its own dynamics, which is creating huge variability by itself, because then you would have a deviation of these two. Okay, so that's all I have basically on the question on more fingerprinting. I think that's really something we have to do more in the proxy or reconstruction community to get these kind of fingerprints, and we also started to work on this in the DSM workshop. Then the question is it relevant what we have here? And I would argue, yes, it is. Just by, you can make a half quantitative study by just rescaling the model variability to look like the proxies. And what you see here is now the ensemble mean of past and RCP for 5 simulations here in black. I think these are like 10-year means. And you can, and then you have the internal variability in the models in orange, and then you have the ensemble spread here in gray. And this is internal variability in the model world. But if you would if you go now to the internal variability from the paleo evidence, so you would scale it up, then it would suggest that instead of this orange bar here, you would have this greenish bar here. Meaning that locally it really matters. If you care, the global warming is still dominating, but if you care, if you want to cross the threshold of 3 degrees somewhere, or if you care, if you want to put some crop somewhere which shouldn't get too cold anymore, then it matters somehow if everything is going monotonously up, or if you can have these variations around this. Okay. Now, the question is it time that we can also look at this in terms of model experiments, or to include this in model experiments? And as I said, you are more the experts here, so these are just like some ideas of somebody not working in this field. The first idea would be, can we use models to prove the proxies wrong or check their physical consistency? And the idea here is that, I mean, we have proxy records in the ocean, which have quite a clear signal that they suggest basically that you have the variability has this kind of scaling behavior, whereas the models show this here. So there is this signal. So we can, on the other hand, for example, in Greenland and Antarctica, they don't show so much variability. And on land, again, they show this kind of scaling behavior. So what we could try, can we make an atmosphere-only simulation where we rescale the sea surface temperature field to show this variability? And then we can look first, does the model just crash? Because we have much more variability inside. And second, how does the variability then look over the land and the ice sheet? So is it consistent to the proxy data or not? Maybe there are also other ways, but the idea would be, can we somehow use the models to, the proxies have quite a strong story of telling that you have this variance mismatch effect of 100. Can we somehow disprove this with the models? The other idea would be, can we also make things like variability storyline scenarios? So we make, for tipping points, for example, we know the probability is very uncertain. So we still make these storyline scenarios to say, in case a tipping would happen, what does it do to the crops in New England, for example, or not in New England, in Great Britain? So can we do something similar? Could we say, let's assume the proxies would be right. How would this affect now the probability of extreme events? How would a world like this look like? Is it completely inconsistent instrumental data? Then we can kick it out, or maybe it's still consistent, but it will still change like probabilities of extreme events, of droughts, and all of these things. So you know better how to do this, but I think what could maybe do is to nudge somehow again the temperature fields to some rescale temperature fields which have these properties of the proxies. And the final idea, which came also up in the workshop, is, can we detune or tune models according to the proxy variability? So the question is, are there like a physics or parameter set that has more centennial variability, but still a realistic last century? And I mean, one might argue, okay, the proxies are too uncertain to do this and to tune your model to this. But on the other hand, it's a justification for the present, like search for stability. And even if we are only like certain by 2/3 or 80%, isn't it still worth to look if this is possible at all? And I mean, from Bakker, we have a starting point where he was modifying the parameters in the model and looked at how this affects variability, in his case, mainly by AMOC. So yeah, the question is this something which would be possible? A bit like the climateprediction.net, but looking at the paleo data as a target. Okay, so to summarize, yeah, so even after reviewing the literature and everything which happened in 10 years, we are still pretty sure that models are underestimating the regional temperature variability in long timescales. We have the systematic dependency of this model proxy agreement on the spatial scale. So that things are suggesting that basically what is happening is that things keep more spatial heterogeneous. And yeah, the call would here be, do we have ideas for the modeling community to jump in this game of looking at the variability? Thank you very much.
Thank you very much, Tom, for this great presentation and the food for thought. Are there clarifying questions? I just see clapping hands. If that's not the case, I think we will have a lively discussion in a moment. Then I'd say thank you, Tom, and I would invite Bo to share her screen. Can't see you at the moment on my screen. Perfect. We see the preview. Oh, and
Do
now
you see the presentation mode well?
Yes, it looks perfect. We can also hear you well.
Great.
The floor is yours.
Yeah. Okay, so I'll take you to the carbon cycle world. So what Tom just talked about, the simulations he was analyzing were mostly driven with prescribed CO2. So our work with carbon cycle, especially for ocean carbon cycle, we want to look at what's the ocean's contribution to atmospheric CO2 variations in the past. So why we look at the ocean? Because the ocean plays a major role in regulating atmospheric CO2. For that, that's because ocean itself is a huge carbon reservoir. How the ocean can contain so much carbon? There are several reasons. First, CO2 can react with seawater. So in nature, aqueous CO2 is only about 1%. And this is the only part that can be used to exchange with atmosphere. So the carbon chemistry brings a buffer for CO2 exchange. The next is the biological carbon pump. So photosynthesis will absorb carbon, and after the organisms die, they sink into the deep ocean and remain, therefore leave a small DIC in the surface and a large reservoir in the deep ocean. And on top of this, there's circulation, which brings the deep ocean carbon and nutrients back to the surface. When we want to model the ocean carbon cycle and use it to predict future carbon sinks, we see problems. So the first one, we know that the model uncertainties exist, and because we have to make simplifications of processes, so-called parameterization. So our analysis or conclusion could be just dependent on how these processes are implemented. Another thing is the biogeochemical models are tuned usually against present-day observations starting from the late 20th century. It's a very short period, and it's so short to constrain the long-term processes. Especially if we come back to this page, the deep ocean DIC has a long time scale on affecting atmospheric CO2. So how to solve this? In our project, we have a good opportunity towards tackle these problems. And we here use two approaches. First, we do a model intercomparison study with simulations for the past climate. So we can compare how they implement, how parameterization affect our conclusions and how robust are the conclusions. Another approach is we want to conduct transient simulations for the last deglaciation. So about 20,000 years long simulation. And we also would like to compare to data so that we can better constrain the transient behavior of the ocean biogeochemistry. So this is how my talk is organized, and is to be in two parts. So the first one is the ocean biogeochemical model intercomparison study. In the current phase, we focus on LGM, so about 20,000 years ago. So the central questions we want to address now is which processes draw down CO2 at LGM and by how much? And do models agree or disagree on the findings, and why is it? So there are 3 ESMs participating and also one EMIC participating in this MIP study. So RV ESM at RV, CSM used at Maroon, MPI ESM used in our institute and also in Keele University. And we use different physical tuning and also different marine particle sinking schemes. Clamber X is used as PIC. So when we come to model intercomparison for carbon cycle, a common protocol is vital for interpreting and comparing the data. So in the LADI 2021 paper, they already found the incomparable results can be due to lack of protocol. So in these figures, Each arrow shows the change from pre-industrial to LGM of inventory or mean concentrations. So here in gray shading is the prescribed CO2 setup. In black are the prognostic CO2 setup. And in brown is prognostic CO2, but with increased LGM inventory. So you can see the errors scatter everywhere, just depending on the choice of model setup and alkalinity inventory. And in our simulations with MPI ESM, we can see with or without a sediment model, there's also quite some differences in alkalinity distribution, and alkalinity is a key factor for ocean carbon sequestration. So for this MIP study, we first identified a common protocol. So we use prognostic CO2 for the carbon cycle, and we still use prescribed CO2 for radiation. Here we focus on the ocean's impact, so we exclude the land carbon CO2 fluxes, and we don't consider a sediment module. So in this case, the flux to the sediments of the particulate matters are immediately dissolved at the bottom ocean. And then we conduct 3 types of simulations: pre-industrial control, LGM PMIP type of simulations. So we apply LGM boundary conditions, and we use the same inventory of carbon, alkalinity, and nutrients as pre-industrial. And we conduct another LGM simulation to get low CO2. For that, we either increase alkalinity and DIC with a 2:1 ratio, so to mimic the dissolution of sediment calcium carbonate, or we increase only the alkalinity inventory. So here's some preliminary results. Here I'm showing the atmospheric CO2 concentration in the different simulations we defined. What we can see is if we conserve the inventories of alkalinity, so comparing pre-industrial and LGM PMIP type simulation, we see a decrease in atmospheric CO2, and this is mainly due to solubility pump. It's still far away from the 190 ppm. And with adding alkalinity, all models can lower CO2 to the desired value. So this is robust in all models we show here. Next, I would like to show you the distribution of the DIC in the interior ocean. So next, I'll only focus on these simulations and the first 3 models. So here I'm showing the difference between the LGM PMIP type simulation to pre-industrial and for zonal mean values in Atlantic, Pacific, and Indian Ocean. So what we can see here is in both MPI models, increased DIC is mainly in the southern south water, and this is due to the reduced air-sea exchange. And in this weak LGM AMOC version and Climber X, because they have a shallower and weaker AMOC, they can store more DIC in the deep Atlantic. And so when boosting alkalinity, the pattern is the same as the PMIP type simulation. And to look at more details, we compare these 2 LGM simulations, and we can see boosting alkalinity mainly increase DIC in the bottom water. And there's a bit more accumulation in the MPI models and more vertically homogeneous in the Climber X model. So how does it compare to data? Here we conducted a first comparison to carbonate ion concentration proxy data. So clearly with a weak and shallow AMOC in this MPI ESM version and Climber X, the negative anomaly is captured in the deep Atlantic, and with the strong LGM AMOC, this cannot be captured at all. But in this MPI case, the deep Pacific probably simulate a too low carbonate ion concentration. So when boosting alkalinity, we see it's not really helping to maintain the agreement with carbonate ion concentration data. So to bring things together and look at the mechanism to contributing to the carbon storage in the ocean, here we are going to compare to this proxy-based analysis. So on the starting point here is the DIC and alkalinity concentration in the modern ocean, and here's at LGM. And this change is contributed by the ice volume change. So they, with reducing ocean volume, the concentration of tracers. And they increased respired carbon in the deep ocean and calcium carbonate dissolution. So how does it look like in our models? So in the PMIP type simulations, we see the three models we just showed as scattering everywhere. And we will still go into details to look at what is exactly the impact, the circulation or the biology. And so the main mechanism to drive DIC storage in the LGM ocean is to boost alkalinity. So this is consistent in both the Pacific values and for the global ocean. So to conclude this part, we see with the conserved alkalinity inventory between LGM and pre-industrial, our models simulate a glacial CO2 drawdown by about 5 to 40 ppm, and this is mainly due to the solubility pump. Our models consistently show that boosting alkalinity can lower atmospheric CO2 to about 190 ppm, and with a similar value of the added alkalinity. The distribution of DIC and carbonate ion differ among models, and this is due to the different circulation states in the model. So next, we identify some directions to improve our LGM simulation. And the first thing we would like to do is to increase respired carbon in the LGM ocean. How to do this depends on the features of each model. For example, in the MPI ESM model, we see that the primary production is quite low at LGM because the growth rate is very sensitive to temperature. So this is the direction, one direction we would like to take for the MPI model. And another thing we will consider next is further model data comparison, because we all simulate C13 and C14 in our models. So it will be another assessment of our simulations. Okay, I come to my next part. The transient simulations for the last deglaciation. So here, the runs are only with MPI ESM. So as I already mentioned at the start, we want the transient simulations for long-term can help to constrain the long-term processes that cannot be done with the CMIP type simulations. Other advantages of transient simulations are also to investigate abrupt events like Heinrich events or boiling Arrow warming and the cascading effects. They also help to study the leak-lag relation between different components or processes. So in this study, we would like to address two questions. So in a transient run, what is the processes driving the deglacial atmospheric CO2 rise in the model? And what is the impact of model tuning and the sediment module on the deglacial variation of ocean biogeochemical variables? So for this, we conduct two runs with two model versions. So they have the same physics, but with different model tuning and with or without a sediment module. So in the first model, it was one of our very first transient runs. So we still prescribed atmospheric CO2 for both radiation and carbon cycle. and we have a sediment module on. In the second model version, which actually follows the PMIP, the MIP protocol I just mentioned, we use prescribed CO2 for radiation, but prognostic CO2 for carbon cycle. Here only air, ocean, air, sea flux considered. And a bunch of parameters are tuned, and the sediment module is switched off. Both models for the ocean biogeochemistry has been validated with present-day observations in their control simulations. In the transient runs, we prescribe ice sheet, and with the increased rising sea level and discharge of meltwater, the automatic adjustment of topography, river routing, and land sea mask is computed following the algorithms developed in our physics group. And we also implemented a computation for the automatic adjustment for biogeochemical tracers. Okay, so here I'm showing the atmospheric CO2 in gray is the prescribed CO2 for radiation. In dark blue is the prognostic CO2 in our B2 model. So clearly we are still far away from what we want to achieve, but the first analysis will help us to understand the model behavior and know what to improve in the next runs. Here I do analysis of the surface PCO2 change between 21 and 6K. And here we can see the deglacial CO2 outgassing in this model is mainly by warming, which contributes about 24 ppm. And the variation of surface alkalinity and DSC has a relatively small contribution. And comparing the LC CO2 flux, we can see in B1 model, which uses prescribed CO2, the CO2 flux is mainly masked by the prescribed CO2 in the atmosphere. So next, I would like to show the variation of the primary production, which has a large impact on the vertical distribution of DIC and therefore could impact the surface DIC and CO2 exchange. So in the two models, we can see they are both showing increasing trend, mainly due to the warming and a higher phytoplankton growth rate. Here in, So here in the gray circle, I'm showing the observation or observation-based estimate of a global net primary production. In these horizontal lines, is the value for our from our control simulation, where we did the tuning and validation. So both models were well tuned with present-day observation, but through the deglaciation, we can see they are apart quite a bit. In particular, in this B2 model in dark blue, so at entering pre-industrial times, the NPP is much larger than what was tuned in the time-slice control runs. And this is probably because with this model tuning, there's a faster cycling of organic matter in the surface ocean. And this can be illustrated by a smaller ratio of export to net primary production ratio, and it's decreasing even more through deglaciation. And so if we look at surface phosphate, actually both models were doing quite well in capturing the present-day observations. So alkalinity is another key factor for surface for atmospheric ocean CO2 exchange. But we can see in these two models, they show quite different trends, with one model going really high, the other is slightly going down. So in this B2 model at pre-industrial, we get a higher alkalinity value than the control run. This is because in this run, we boosted alkalinity to get a lower CO2. And in this run, there's a lack of mechanism to remove it. And in the B1 value, in the B1 model, which simulate a very large increase in alkalinity through deglaciation, and we found that this is mainly due to the input sedimentation imbalance of both alkalinity and silicate. So when we include a sediment module in the model, then we have to prescribe input as a surface to compensate the loss to the sediment. Otherwise, the ocean volume will show large drift over the spin-up time. And this is what we did. And for the LGM spin-up runs, for the deglaciation, we just kept these constant input values through the deglaciation. So the loss of calcium carbonate to the sediment is larger at LGM. This is because the oversaturation of carbonate ion with the smaller ocean volume. So the input of carbonate ion is larger at LGM than pre-industrial. So if this value is kept constant through deglaciation, there will be accumulation of surface alkalinity. And something similar happening for silicate. So the loss of OPO to sediment is larger at LGM also. And this is because OPO dissolution rate is lower at lower temperatures. And with the sea surface warming, the excess silicate input will boost OPO production. And when OPO production increase, the calcium carbonate production, when OPO production increase, this will reduce calcium carbonate production and therefore leave more excess alkalinity in the surface ocean. So together, these two will contribute to this very large increase of alkalinity through deglaciation. So I want to stress that this is a model feature which evolve naturally in the model, and this can only be shown in long-term simulations for the past climate. Okay, so to conclude this part, we find in MPI ESM, the deglacial oceanic CO2 outgassing is mainly driven by the solubility pump. The deglacial variation of NPP is sensitive to biogeochemistry tuning, but variables such as surface phosphate is not sensitive. And we find surface alkalinity and sediment cycling are strongly affected by a sediment module. So this suggests what we can do to improve the simulations next. So one thing, as already we found in the first part, is the too low respired carbon at LGM. And another thing is to still tune the model and adjust the model regarding the input sedimentation imbalance of silicate and alkalinity. And with this, we can make use of the recent study by Fanny Ladi. So here she used the transient simulations variable of temperatures, precipitation, river runoff to compute the weather fluxes of alkalinity through deglaciation. And this is something we can make use of or tune the model, as a target to tune the model for that. Okay, that's it. Thank you for your attention.
Thank you very much, Bo, for this great presentation and a deep dive into carbonate chemistry. Do we have questions that are directly related to Bo's presentation and clarification? If that's the case, then please raise your hand or raise the voice. I would stop the recording now